We know that extrinsic semiconductors are of two types, p-type and n-type. And p-type have excess of holes compared to electrons as charge carriers. And in n-types, you have majority charge carriers, electrons, and minority charge carriers, holes. So I have a question for you. Is p-type semiconductor charged and is n-type semiconductor charged? What do you think? Can you call a p-type semiconductor and n-type semiconductor charged? Are they charged? In fact, the p-type and n-type semiconductors are not charged. They are electrically neutral. Why? How do we get a n-type semiconductor? We get a n-type semiconductor when we add a pentavalent impurity to a crystal lattice. Like here you can see +4 means the nucleus of a silicon or germanium, whichever pure semiconductor it is. To that we are adding a pentavalent impurity. So when we add a pentavalent impurity, what happens? The pentavalent impurity has 5 electrons in its valence shell, right? So it will share 4 electrons with the neighboring atoms and 1 is free. So this is the extra free electron which is available for conducting electricity. But when we added the pentavalent impurity, it was a neutral atom and it contains equal number of protons in its nucleus and equal number of electrons in its orbiting shells. So the number of protons was equal to number of electrons and it was electrically neutral. When we add it to the crystal lattice, again the nucleus is same, C plus 5. So this extra electron, including that, it will have 5 electrons in its outermost shell. So as a whole, even if one of the electron is free for and available for conduction, the total charge is not changing. So a n-type semiconductor is neutral because this extra electron is not added as an extra charge. It is part of a neutral atom. So its charge is balanced by the number of protons in the nucleus. So if you take the crystal as a whole, the n-type semiconductor is not charged. So in n-type semiconductor, the excess electrons are given by the donor atoms, that is the pentavalent impurity atoms, which are electrically neutral. So we are not adding a charged particle or we are not just adding extra electrons to the crystal lattice. So it is electrically neutral. Now let us consider the case of a p-type semiconductor. How do we get a p-type semiconductor? By adding a trivalent impurity, right? Which means an atom having 3 electrons in its valence shell. Now when it enters the crystal lattice, 3 of the electrons gets shared with the neighboring atoms and there is a vacancy or it is unable to share with the fourth neighboring atom. So this vacancy of an electron or deficiency of an electron will act as a hole. So electrons from the neighboring atoms can jump to this position. So this is a hole. So here again, when we added the trivalent impurity atom, the atom as a whole was neutral. So the acceptor atom or the trivalent impurity atom added had equal number of protons and electrons. So they were electrically neutral. Now when we add it to the crystal lattice, it's not going to affect the neutrality of the crystal because it's a neutral atom entering a neutral crystal. So again, it will not change the polarity of the crystal. So p-type semiconductor is also not charged. Both of them are electrically neutral. So p-type and m-type semiconductors are electrically neutral. This is a MCQ question which usually asks, for example, they may ask, what is the charge of a p-type semiconductor? And they will give options: positive, negative, neutral. So which one will you choose?
Neutral.
Neutral, because the children, they have a tendency to think that a p-type means positive, n-type means negative. There is nothing like that. Both p-type and n-type semiconductors are neutral. Is this concept clear to you?
Yes, teacher.
Okay, now let us see what happens when we join this p-type and n-type semiconductor. So, semiconductor diodes. Di means what? Two. So, diodes means they have two types of materials. One is the P type and another one is the N type. So, the junction, the point where both of them join, is called the junction. So, today we are going to learn about p-n junctions. That is the junction formed when a p-type semiconductor and n-type semiconductor is combined. So there are two terminals. That is why it is called diode. A diode or p-n junction is obtained by combining a p-type and a n-type semiconductor. By mistake, I typed diode. P-type and N-type semiconductor. Now, how can we make such a combination? In actual case, what we are doing is we take a crystal, a pure semiconducting material, for example, germanium or silicon, then we dope or add impurity to make N-type semiconductor on one region. That is, we add a pentavalent impurity on one side. And on the other side, we add some trivalent impurity so that a P region is formed, or a P-type semiconductor is formed on the other side. So we have a single crystal of semiconductor, pure semiconductor, and we have added pentavalent impurity to one side and trivalent impurity to the other side. So the region where we add the pentavalent impurity becomes N-type semiconductor. There will be electrons as the majority charge carriers, and there will be more extra or free electrons available for conduction. And in the region where we added the trivalent impurity, it becomes a p-type semiconductor with large number of holes available for conduction. So holes as majority charge carriers. So this is how we make, and the region in between becomes a p-n junction. Now let us see what happens in this p-n junction. So how do we get a p-n junction? A pure semiconductor is doped, means impurity is added, such that a p-type is formed on one side and a n-type is formed on the other side. And the middle region forms the p-n junction. Now let us see what happens at the junction. Now, we know that this pentavalent impurity, when it loses its electron, this will become a positive ion because it had equal number of electrons and protons. So, the number of protons in the nucleus was equal to the number of electrons surrounding it. Now, when one of the electron become free, what happens when an electron move away from an atom? It becomes a positive ion, right? So when one of the electrons become free, in effect, this atom, the pentavalent impurity atom added, acts like a positive ion. Similarly, in the other region where we have added trivalent impurity, it gets a hole Hole means it can accept a electron, right? So when it accepts a electron, what happens? A electron is added to that atom, extra, because when it was a free atom, it had equal number of protons and electrons, and it was neutral. Now, when it is added to the crystal lattice, other atoms see there is a vacancy and an electron is added to that atom. So what happens when a free electron is added to an atom? It will become a negative ion. So here in the p region, in effect, those impurity atoms acts like a negative ion because an electron is added to them. It can accept an electron, so it behaves like a negative ion. Now, near the junction, as soon as the P and N type semiconductors are formed, what happens? A PN junction is formed. What happens is the holes try to move to this side and electron try to move to this side, and in the middle region where they have combined, what happens? Where they have combined, here there was an extra electron, right, with the this p type pentavalent. So what happens? It will go and take the position which was vacant near this trivalent impurity. So this becomes a positive ion, this becomes a negative ion. Similarly, this becomes positive ion, this becomes negative ion. So in the middle region, instead of extra free electrons and holes, they combine together and there are no extra electrons or holes, free electrons or holes. What we have is positive charged ions and negative charged ions, and they are heavy nucleus or atoms, so they cannot move, they are not mobile, they are not light like the electrons. So in the middle region they form a depletion layer or a barrier. So further electron flow from the N region to the P region, or further flow of holes from the P region to N region is not allowed. So there forms a junction or a depletion layer. This depletion layer consists of positive ions from the pentavalent impurity and negative ions from the trivalent impurity. Because the pentavalent impurity free electrons have gone and sat in the vacancy in the trivalent. So this is how a junction is formed in between the P region and the N region. So the electrons from the N region diffuses to P region and holes from the P region diffuses to N region. In the middle, positive donor ions and negative acceptor ions are formed. And this is called the depletion region. Is that clear how a depletion region is formed in between?
Yes, teacher.
Okay, so further diffusion of electrons and holes are not possible unless an external potential is applied. So here the electrons cannot move to the side because here there is a layer of positive ions. They will push back the electron. They will not allow the electron to come because they will repel the electrons because they are positive ions, right? So they will repel the free electrons and not allow them to come to this side. Here you have a layer of negative ions. So when the holes which behave like positive charge try to pass, what happens? They will, I'm sorry, this negative ions will repel the electrons and the positive ions will repel the holes. So what happens? The electrons and holes cannot pass each other. So they cannot diffuse unless an external potential is applied. Now here, look down. This is the symbol for a PN junction diode or a diode, simply called a diode. This arrow region is the P-type side. and this dash or this line is the n-type side. Usually the p-type side is called the anode and the n-type side is called the cathode. It is called plus and minus, but remember p region is not positively charged. N region is not negatively charged. Still, this is expressed as positive and this is expressed as negative. Don't get confused with that. Expressed as positive just means it is p-type and expressed as negative just means it is n-type. They are not charged. And in actual case, the diode is too small. See, it looks like this. So when you get this device, the black region, which is broad, is the p-type. And a silver color or hash colored line shows it is the n-type. Sometimes the p-type is called the anode and the n-type is called the cathode. Is it clear to you? This is a diode in practice. It's very small. Is it clear to you how to represent the diode in a circuit? This is the symbol and this is the actual diode. Can I
Yes,
move
teacher.
forward?
Yes, teacher.
Okay. Now let us see what happens when we apply some external potential. So when we connect a diode to an external circuit, there are two ways in which you can do that. One is called the forward bias and the other one is called the reverse bias. So what is forward bias and what is reverse biased? Here you can see a forward bias connection. Here you can see a reverse bias connection. In forward bias, positive terminal of battery is connected to p-type and negative terminal of battery is connected to n-type semiconductor. Here see, the positive terminal of the battery is connected to the p-type and negative terminal of the battery is connected to the n-type. Now when you see the circuit, here see the positive terminal of the battery is connected to p-type. I told the arrow mark shows p-type and the line shows n-type. So the negative side of the battery is connected through a bulb to the n-type. So this is p-type and this is n-type. So in forward bias, p-type to positive, n-type to negative. Okay. Now what happens when we make such a forward connection? Now when you connect this, as I told before, here in this figure, this golden balls represents the free electrons and the silver balls represents holes. We know that in p-type region, the majority charge carriers are holes, the silver balls. And in an n-type region, the majority charge carriers are electrons, the golden balls. Okay. Now, if there was no connection, because of this junction, the holes cannot diffuse to the end region because this layer of positive ions here will not allow it to come. It will prevent or it will repel the holes from entering the end region. Similarly, the balls, golden balls or the electrons cannot enter the p region because this negative ions. They will repel the electrons and do not allow them to enter the p region. So here, due to the depletion layer, there is a barrier, repulsion for the holes in the p region and the electrons in the n region. Now, when you connect it to the battery, okay, so there is a positive terminal here. So when you connect the p-type to positive terminal, from the p-type, positive terminal, it will push the holes towards the depletion layer and the n-type region. Suppose this depletion layer applies 2 Newton repelling force towards the holes and the applied terminal gives 3 Newton force to the holes to go to that side. What will happen? The depletion layer is giving 2 Newton repelling force to the p-type, to the holes. And the positive terminal is giving, what did I tell? 2 Newton, right? So it is getting 3 Newton. So more force is applied by the battery. Then what will happen? The holes will move. So similarly, if 2 Newton force is given to the electrons in the end region, what happens? It will repel. And if the battery is giving a higher force, pushing the electrons, because this is negative, so it is pushing the electron with more force towards the other region. So what happens? The depletion layer will not exert enough force to oppose the applied electrical force, and therefore they will move. The free electrons will move towards the p-type, holes will move towards the n-type, and conduction of electricity will happen. So when it is forward biased, what happens? The electricity is conducted, or there will be a flow of current through the diode. See, now the arrow mark is in the direction in which the current flows. So if it is connected to positive, what happens? Current flows in this direction, and see the bulb glows. So when you are forward biased, the depletion layer is very thin, it becomes very thin, and the PN junction offers very low resistance, and an ideal diode has zero resistance, which means the current will flow completely through an ideal diode if it is connected in the forward bias. Is it clear to you how current flows when we connect a PN junction diode in forward bias? Is it clear?
Yes, teacher.
I have one question.
Yes, please ask, Hasina.
Why will the depletion region in the forward bias be narrow?
It becomes narrower because, see, here, suppose it is, I will take the previous picture. Here, see, suppose there are positive and negative ions, right? Now, when you connect this to a battery, what happens? The electrons are pushed because N-type region is connected to negative terminal, P-type to positive terminal. So more hole can come to this side and more electrons can come to this side. So they are no more neutral atoms. So this electrons can come to this side and holes can come to this side. So the barrier becomes thinner and thinner. Barrier becomes very thin and thin. That is how it becomes thinner. And you will get more idea when we consider this reverse bias and compare. Okay, let us compare this and then I will tell you again why this is thin and this is thick. This word thin is used in comparison with the other one, reverse bias. Okay, let us see what is reverse bias and then see, Hasina, whether the doubt persists for you. In the reverse bias, the positive terminal is connected to the N-type and negative terminal is connected to the P-type. So when the positive terminal is connected to N-type, anyway, there are negatively charged ions here. So they are pushing the electron away from the depletion region. This positive terminal is attracting the electron towards it, which means they are again pulling the electrons away from the depletion region. So what happens? The electrons will move towards the positive terminal. So more and more electrons are moving away, which means more and more electrons are moving away. So the depletion region will widen itself. See here, These are positive ions because their valence electrons are moved away from them. See, they become positive ions. They are pentavalent. They becomes positive ion because their free electrons are taken away from them. So there are more and more positive ions formed here. So the depletion region widens. Here, similarly, the p-type is connected to the negative terminal of the battery. So from the negative terminal of the battery, electrons will come and occupy the position of the holes. So the holes in effect move away from the depletion region. Already the holes are not allowed to come to the other side because they are repelled by the positively charged ions. Now this repulsion, in addition, there is a pulling of the holes towards the negative terminal of the battery, which means the electrons from the battery are going and occupying the hole positions. So these are the trivalent impurity atoms. So they are accepting the electrons, acceptor atoms, accepting electrons and becoming negatively charged ions. So in the depletion layer, what happened? More and more negatively charged ions are formed. So when you connect in the reverse bias, the depletion region widens, which means more and more neutral, not neutral, ions are formed on both sides. So we can compare and tell that in a reverse bias, the depletion region becomes thicker and thicker, which means it widens. While in a forward bias, the depletion region becomes narrow. So this thick and thin is a comparative statement. Is that clear, Hasina?
Yes.
Okay. So this words are comparative. So this is how the depletion region widens when there is reverse bias. So when they widens, the PN junction offers very high resistance. So can current flow through them? No, because the depletion region or the barrier to the flow of current is widening. So PN junction offers high resistance and an ideal diode have infinite resistance, which means they will not allow current to flow through them. So here the current flow is in this direction, positive to negative always, right? So if the current comes in a direction opposite to the arrow mark, no current is flowing. See, the bulb will not glow. So you can just remember that in forward bias, positive terminal is connected to p-type, negative terminal is connected to n-type, and the current will flow. But in reverse bias, the positive terminal is connected to the negative terminal, positive terminal is connected to the n-type and negative terminal is connected to the p-type and the current will not flow. So is that clear? How we can bias a circuit? Forward and reverse bias. May I
Yes.
continue? Okay.
Sure.
So I would like to discuss one more thing about this, the characteristic curve of PN junction. So what is meant by the characteristic curve of a PN junction? The representation of variation of electric current with change of voltage of a PN junction in a graph is called characteristic curve of a PN junction. So characteristic curve means a current voltage graph drawn for a PN junction. So current is taken along the y-axis and voltage is taken along the x-axis. Now, this shows the forward bias region, positive direction of the x-axis. So, this shows the forward bias region and negative direction of the x-axis shows the reverse bias. Forward bias means The positive of the battery is connected to P type and negative of the battery is connected to N type. So in the beginning, there is a very thin potential barrier, right? So no current is obtained in the beginning due to the small potential barrier. So in the beginning, so if we apply a very small potential, then it cannot overcome that barrier. I told you that when we connect, what happens? There is a small potential barrier. It should overcome so that the charges can flow, electrons and the holes can flow through the barrier. So in the beginning, there are no current flowing because of that small potential barrier. But when the applied voltage is more, it can overcome the barrier, then currents start increasing steadily. So here you can see initially when the applied voltage is very low, the forward current is very low. There is no forward current. But once it is more, what happens? The currents start increasing in the forward bias. Now, this small potential which need to be applied is 0.3 volt for germanium, which is a semiconductor, and it is 0.7 volt for silicon. So when the applied potential, forward potential is more than that, the current start increasing. And see, the current is of milliamperes. Current is only in terms of milliamperes. Now, when the applied potential crosses this particular value, it is called the threshold voltage, cut-in voltage, or knee voltage. These are the terms. The current starts to flow and increases exponentially very quickly. So what is the knee voltage for germanium? 0.3 volts. And what is the knee voltage for silicon? It is 0.3 volt. Knee voltage is sometimes called the threshold voltage or cut-in voltage. Now what happens in the reverse bias? Now, due to minority charge carriers, a small current called reverse current flows. See, compare the current in the forward and reverse. See, forward current is in milliampere, while the reverse current is in microampere. Okay, so due to this minority charge carriers, there will be very small in the micro region, in the reverse bias region. And as the on increasing the reverse voltage, a sudden at a very high voltage called breakdown voltage or Zener voltage, a large amount of current, still it is in the microampere region, is obtained as if the PN junction is completely broken down, which means when you increase the voltage, this depletion region widens, and all the impurity atoms becomes ions. Okay, so it is no more a extrinsic semiconductor. It loses its property as an extrinsic semiconductor. It behaves like an intrinsic semiconductor with only minority charge carriers and very low current flowing through that. So we call that the PN junction have broken down. Okay, and that voltage, high reverse voltage at which it occurs is called the breakdown voltage or the Zener voltage. Is this clear to you?
Yes, teacher.
Okay, so we will stop here.